How to teach quantum physics to your dog. Sounds kind of crazy, right? But that's exactly what we're going to try to do today. We're diving into this amazing book by physicist Chad Orzel. And believe it or not, we're going to try and make sense of the quantum world, all through the eyes of a dog.
And this is our guide, Emmy. So the story goes, when Chad Orzel adopted her, he found out she could talk. And you know what her biggest concern was? The critter situation in the neighborhood. She really likes bunnies. And it's this simple, totally charming perspective that's going to help us unpack some seriously deep stuff. So yeah, the whole idea is pretty straightforward. Orzel just uses his chats with Emmy to turn all this abstract quantum mechanics stuff into everyday things we can all understand. You know, squirrels, bones, and yep, lots of bunnies. So let's see what Emmy has to teach us, shall we? All right, our first big idea is a weird one. Seriously, at the quantum level, the universe just doesn't seem to care about the difference between solid things, particles, and spread out things like waves. This is called particle-wave duality, and this is exactly where everything you think you know about the world starts to get a little fuzzy. I mean, in our world, the difference is super obvious, right? A particle, let's say it's Emmy the dog, she's in one spot. If there's a tree in her way, she's got to pick a side to go around it. Simple. But a wave, like light or sound, that's not in just one place. It spreads out, it can bend around that same tree, and in a way, it takes all the paths at the same time. And this isn't just a theory. This was actually proven way, way back in 1799. A guy named Thomas Young did this famous experiment where he shined light through two little slits. And what he found was wild. You don't just get two bright lines on the other side. Nope. The waves of light actually interfere with each other, creating this whole pattern of bright and dark stripes. That was it. The proof that light is a wave.
Okay, fine. Light is a wave. Got it. But what about something we know is a particle, like a single electron? Surely that little thing has to act like Emmy the dog and just pick one slit to go through, right?
Well, about that. In 1927, two scientists, Davison and Germer, found something absolutely mind-blowing. They fired electrons at a crystal, and they got that same interference pattern, just like the light waves. The only possible conclusion was that tiny particles can also act like waves. And get this, everything has a wavelength. You, me, this desk. It's just that for big stuff like us, it's so incredibly small we could never ever notice it. Okay, so if particles can be spread out like waves, things start to get, well, fuzzy. And that leads us right into our next big brain-breaking idea. There's a hard limit on what we can ever know about the universe. And of course, Emmy has the perfect way of putting it.
It all starts with a very dog-like question. Where's my bone? But in the quantum world, that simple question leads to a really strange place. Because down there, the very act of looking for something changes it.
And this is the famous Heisenberg uncertainty principle. Let's go back to the bunnies. Imagine you're trying to track a really fast one. To see exactly where it is, you have to bounce something off of it, right? Let's say a little particle of light, a photon. But the moment you do that, you give the bunny a little nudge. That changes its speed and its direction. That's its momentum, and you can't predict by how much. So you can know where it is, or you can know how fast it's going, but you can never know both of those things perfectly at the exact same time. And listen, this isn't because our measuring tools are bad. This is a fundamental, unbreakable rule of the universe, and it's all wrapped up in this famous equation. It basically says that the amount of fuzziness in the position, that's the delta x, times the fuzziness in the momentum, delta p, can never, ever be smaller than a certain tiny number. It means there's a blurriness that's literally baked into the fabric of reality. The book puts this so well. Emmy says she buried her bone 16 steps from the big oak tree, give or take a step. See that? That give or take a step is the uncertainty in its position. That's the delta x. And what the principle says is you can't make that give or take for where it is and the give or take for how fast it's moving both zero at the same time. It's just not possible. Okay, you ready for our last concept? Because this one might just be the weirdest of them all. And it involves a dog, a fence, and what feels like a little bit of quantum magic. It's called quantum tunneling. Look, in our world, if you don't have enough energy to get over a hill, you're stuck, right? You just can't get to the other side. But in the quantum world, a particle can kind of borrow a little energy from that uncertainty we were just talking about and just pop up on the other side of a barrier that it should never ever have been able to cross. So think of it this way. Emmy wants to get to the other side of the fence. She doesn't have enough energy to jump it. She doesn't dig under it. But quantum mechanics says that there is a tiny, tiny, non-zero chance that she could just, poof, appear on the other side. Now, for a dog, the chances are so small it's basically zero. It'll never happen. But for something tiny like an electron, it happens constantly. So at this point, you might be thinking, okay, this is all really weird, but so what? Why does any of this matter? Well, it might sound like a weird philosophical game, but these bizarre rules are actually the foundation of our entire modern world. I'm talking about some of our most advanced tech. Take that crazy tunneling thing we just talked about. That's the principle behind something called a scanning tunneling microscope, or STM for short. And what does it do? Oh, nothing much. It just lets us literally see individual atoms. So here's how it works. You take this super sharp needle tip and bring it unbelievably close to a surface. I mean, nanometers away. The electrons on the tip don't have enough energy to jump across that gap, but a few of them tunnel through anyway. And by measuring that tiny little electrical current of tunneling electrons as the tip scans around, the microscope can build a perfect map of the bumps and dips of the atoms themselves. And the results are just, wow, breathtaking. This is a real image from one of these microscopes. Scientists at IBM actually used the tip of the STM to nudge individual iron atoms into place on a copper surface, creating this circle they called a quantum corral. And see those ripples inside? Those are the electron waves we were talking about at the very beginning, trapped inside the corral. This is insane. We're not just looking at the quantum world anymore, we are literally building with it, one atom at a time. So let's recap our lessons from the dog park. First, things can be both particles and waves at the same time. Second, you can't ever perfectly know both where a bunny is and how fast it's going. And third, particles can magically tunnel through barriers they have no business crossing. And remember, these aren't just wacky ideas. These are the fundamental rules of our universe. And that brings us to a final thought, really. This whole thing, it's not really just about dogs and quantum physics. It's a fantastic reminder that sometimes even the most complicated, mind-bending ideas are just one good analogy, one good story away from finally clicking. It really makes you wonder, doesn't it? What other huge, complex idea is just sitting out there, waiting for the right metaphor to unlock it for all of us?